And welcome to day 2 of discrete mathematics. Now, today we're going to go over some stuff that you may be somewhat familiar with, either from algebra or even from linear algebra, and that's the concept of relations and functions. But we're going to do it from a very low level to start with and then build up. In a remedial algebra class, you're told certain information, and it's not false. No, you're told certain information, but you're usually not given the whole picture. And in linear algebra, you look at it from a very advanced point of view, and it's almost too complicated. So we kind of want to fill in everything. So the concept of a relation. So first of all, what is a relation? A relation basically is a set of ordered pairs. That's it. There's nothing special about it. Now, there's 3 ways a relation, though, can be presented. It can be presented as a set of ordered pairs. So, for example, I'm going to use the letter R, and that's not a script R. That's not the real numbers. R for relation. And R will be, let's say, 1, 4, 2, 6, 3, 10. There's my relation. It's 3 ordered pairs. I can represent a relation as a set of ordered pairs. That's it. I can represent a relation as the graph of those ordered pairs. So my relation could look something like this. 1, 4, 2, 6, 3, 10. There's my relation that way. And thirdly, a relation can be presented in an equation form. So for example, if I gave you the equation of a line, that would represent a relation with an infinite number of ordered pairs. So you would only represent it this way if it was a finite set of ordered pairs. And more often than not, your relation is going to have an infinite number. I would only do it graphically if the graph was easy to represent. And finally, in an equation form is probably the most convenient, especially if it's infinite. And that relation could be the equation of a circle, the equation of a line, a parabola, darn near anything. So when I have a relation, now we want to break up the parts of the relation. So I have input, I have output. The input, as you know, please mute yourselves, guys, as an absolute automatic. If you come to class, mute yourself. Okay, absolutely nothing in between. If you have a question, ask the question. But when I hear background noise and people yelling, that's not good. That's kind of unprofessional. Right? You wouldn't want my mom to walk in the room and start screaming at me. That would look bad. All right, I have input, I have output. The input is always the first coordinate, the output is always the second. But where is the input coming from and where is the output coming from? So in this case, if I gave you a whole bunch of ordered pairs and all of them had integer coordinates and I'm only using the integer coordinates, then we would say our input clearly is coming from the set of integers and our output. The set that the input is coming from is called the domain. The domain is the set that it's coming from. It's not the values that I'm using, it's where I'm drawing the values from. So my domain might be, in this case, capital Z, the set of integers. Now, the second value, does anybody know where that one comes from?
Codomain.
I'm sorry, I couldn't hear you.
Codomain.
Good. This comes from the codomain. That's a term that a lot of people are not familiar with. The codomain is, in this case, it would be Z again. And I'm not using real numbers, I'm using integers. The domain comes, everything in my input is coming from the set of integers, everything in my output is coming from the set of integers. So I have the domain and the codomain. But in lower level algebra, that's not the term you use. What's the term you used in baby algebra for the second number? Anybody? You called it the range. Is the range the same as the codomain? Oh, no. Now, if you've had linear algebra, you would know this. The codomain is where the second numbers potentially can come from. The range is the values you actually used from the codomain. And that's totally a different animal. So in linear algebra, when you're talking about, as a linear transformation, 1-to-1 and onto and all those kind of things, you went from one vector space to another vector space. If you used up the entire second vector space, you said the mapping was onto, but it's only onto if the range equaled the entire codomain. That's a really important concept. That's a linear algebra concept, but the vocab is the same in this class. So the domain and the codomain are where the numbers come from. Okay, it's actually that simple. So it's kind of boring. Another way we do this is we do what's called a mapping. So I have in my domain, I have the numbers 1, 2, and 3. In my codomain, I'm using the numbers 4, 6, and 10. And right now I'm mapping the number 1 to 4, I'm mapping 2 to 6. This is kind of boring, but this gives us impetus for other types of definitions. So for example, if every element of the domain has a unique image, the things here are called the images. So 4 is the image of 1. If I do this and I use them up, then we say that this relation is 1 to 1. Let's suppose I threw in another ordered pair here, just for the heck of it. Now I'm gonna throw in one more. And let's say that I'll use a different color because I'm adding a new ordered pair here. And now let's say I have 4, 10. We'll throw that one in. Okay. So now I'm going to throw a 4 right there. So here's my mapping. This would no longer be 1 to 1 because these guys have the same image. Or another way of thinking about it, everything in the codomain does not have a unique pre-image. That's how we call it going backwards. So the pre-image of 6 is 2. The image of 2 is 6. Again, this is vocabulary that's pretty uniform and universal. So this one here would not be 1 to 1. Now, there's another term that we always use in related to relations, and that's the term function. Now, everybody knows what a function is graphically. We have all sorts of ways of testing things, but the simplest way to determine a function, the simplest way, it's not the formal textbook approach, is something's a function if everything in the codomain has a unique pre-image? No, that's the definition of 1 to 1. Function is that everything in the domain has a unique image. So in other words, when I'm going backwards, that's not the test for function. The test for function is when I'm going this way. So right now, this is a function because every element of my domain only gets mapped to one element. So let me add one more point here. Now I'm going to add, how about 4, 12. I'm going to add one more. Right here. There. Now, is this a function or is this not a function? Anybody want to try that one?
It's not a function.
Not a function because the number 4 has more than one image. It's getting mapped to more than one thing. Now, when I'm just simply looking at a set, that's a little harder to see because what if my set had, like 1,000 points? That's not a really practical way to determine it. Looking at a mapping is easier. And then, of course, the simplest way of all, the way you learned it in remedial algebra, we go back to the graph. So I have, excuse me, 1, 4 and 2, 6 and 3, 10 and 4, 10. That was not a problem. It was the 4, 12 that was the problem. And we called it in remedial algebra, we called it the vertical line test. Actually, it's way simpler than that. When you see a X value repeated, if we're thinking X and Y in this case, when you see an X value repeated, you tend to be suspicious because that means the one input had multiple outputs. And that's always represented when I see points that are vertically located. So if it's possible for me to draw a vertical line and pass through more than one point, that's what we called the vertical line test. And there's nothing wrong with that, but that would require me to draw a graph and all this. An easy way of thinking about it is one input had multiple outputs. That fails to be a function. But you say, but the number 12 only has one pre-image, but that's not the point. Function is going this way. 1 to 1 is the test going this way. And a lot of people confuse those two because they're similar language, but not exactly the same thing. So that's the most basic definition of relation and function. So now let's go a little bit further with this concept. So now I want to build a relation. So let's create a simple problem. Let's say that A is the set of numbers. How about -1, 1, 2. And let's say that B is the set of numbers 1, 2, 3, 4. Okay. So we're going to start with A cross B. So right now my domain is the set A. My range is the set B, excuse me, my codomain, sorry, not my range. My codomain is the set B, and I'm going to create a set of ordered pairs using only these values. I'm not using the whole set of integers now. I'm just using these values. So let's start with A cross B. And that would be the -1, 1, -1, 2, -1, 3. I'm going to write it all out because I need all of this. And then 1, 1, 1, 2, 1, 3, 1, 4. And then 2, 1, 2, 2, 2, 3, 2, 4. Okay, now I'm going to define a relation. Okay, so right now my universe is this set of points. These 12 points are that's all I'm looking at. I'm going to define a relation, and that because I want to introduce the notation that we use. So let's call our relation, how about capital S? So if my input we'll call X and my output we'll call Y, just to make it easier. So we will say that X, S, Y. That means X is related to Y, S being the relation, if and only if, and sometimes we do a two-way implication symbol, if, let's say, if Y equals X squared. Okay, so as we go through, we can test each pair one at a time. So starting with the first pair, is -1 S1. Is -1 related to 1 based on this definition? Anybody? Just simple yes or no. Is -1 related to 1?
Yes.
Yes. Okay, let's do the next one. Is -1 related to 2?
No.
No, so we would say it like this. We just go like that. Now, we can do this for all 12, but it's kind of easy for us to just look through them. So if I said, then which ones are actually related? I want to write S as the actual set. Remember, I said the relation is a set. -1 is related to 1 because 1 is equal to the square of -1. -1 is not related to 2 because 2 is not equal to the square of -1. So as I went through and did for all 12 of these, it's pretty easy to just do it by inspection. Which of these ordered pairs would fall into this relation? Well, I'm pretty sure we could say -1, 1. No, no, no. Yes. No, 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 no. Yes. So I'm going to be lazy. These are the only 3 ordered pairs that satisfy this statement here. So clearly, S is contained in A cross B. That should be very, very obvious. S can't be bigger than A cross B. S cannot have ordered pairs that are outside of this. So S is a relation, and it's a relation that's defined this way. This is my set of points. So if I went through, for example, 2 is not related to 1 because 1 is not the square of 2. So I can do this. Now, a lot of you, when you do the quiz, will write this out for every single pair. That's okay. It's kind of overkill. I think inspection is probably the easiest way, but I don't want to miss anything either. Now, with that said, is S a function? Anybody want to try that? Is S a function?
No.
I'm sorry, couldn't tell that was a yes or a no.
No.
I mean, I'm hearing both yeses and nos. Well, is there any input that goes to multiple outputs? See, the only inputs I'm using are -1, 1, and 2. Now, both of these went to 1, but each of these went to a unique element. In other words, -1 only went to one value, 1 only went to one value, and 2 only went to 1. I never repeated an input. So actually, yes, this is a function. What it isn't is it's not 1-to-1. Now, graphically speaking, when something isn't 1-to-1, how do I know graphically? See, we said failing to be a function means you fail that vertical line test. How do you fail being 1-to-1?
You have a horizontal line.
You fail horizontal, yeah. And by the way, think of a parabola. right? A parabola would fail a horizontal line test, but we still consider it a function. Oh, that's because two different inputs can give me the same output. If I square the number 3, I get the same values if I square the number -3, but it's still a function. It's just not one-to-one. I can't work backwards and get a unique answer. So if I started with 1, I can't work backwards and get a unique element. But this is a function because every input has a unique output. That, again, that's the simplest definition. That's not the textbook one. The textbook one's okay, but it's a more complicated version that requires, almost cleverness. I'm not a big fan. I like using input and output as the results. So this is a fairly simple notion. So again, my domain is whatever my input's coming from. My codomain is whatever my output's coming from. Now, in this case here, if I asked you what is the range, what would the range be? If the codomain is 1, 2, 3, and 4, what would the range be for this particular relation? The range. I mean, just look at our relation. What would our range be?
3.
Just 1 and 4. Because those are the only ones I used. So if we now think back to baby algebra, because this is very important, this relates to the most basic part of algebra, it relates to calculus. Whenever you are doing, let's think remedial algebra, you're graphing lines, you're graphing parabolas, you're doing simple stuff. Generally speaking, if you called your function f of x, then we'll say f. We write it like this: f was mapping the real numbers to the real numbers. For those in who've had linear algebra, you're familiar with that type of notation. My domain was R, the real numbers, my codomain was R. This is for every conceivable graph you could ever come up with in 2 dimensions. You would always start with that. Why? Because remember, when we do R cross R, that gives us the entire XY plane. That is 2 dimensions. And we actually call that, like we said yesterday, that's called R2. So if my inputs are coming from the reals, my outputs are coming from the reals, I now have the entire XY plane, the infinite XY plane. That's what I'm starting with before I even tell you what my function is. Okay, so now when I give you a specific function, okay, let's say my function was f of x equals x squared. Let's say that's my function. Am I going to use the entire set of real numbers in that codomain? No, I'm only using the non-negative ones because I'm never going to get a negative output. That doesn't change my codomain because the next graph might be, I'll call it g of x. G of x might be the natural log of x. Oh, now I'm not using the whole set here as my input, but I am using the whole set as my output. I'm getting all real numbers as my output. Every time I give you a new definition, it would change which values I'm using. But I'm starting by always saying, this is where they can potentially come from. They can't come from the complex number plane, for example, or I'm not excluding positive numbers or excluding negatives or anything else. So every time you ever did a graph in anything algebra through calculus, you always started with this, and then the specific function you chose is going to limit the values you use. Okay, but not the other way around. You don't start by saying, I'm going to limit the values and now think of a function. So this is kind of universal. And again, when I say domain, codomain, the Cartesian product now is where I'm choosing my points from for my specific thing. So in the example that we just did a moment ago, our Cartesian product produced 12 ordered pairs. Our relation only used 3 of them. This would produce the entire XY plane, but the particular function you might be using might not use every single one. And that's okay. It's a fairly simple notion, but the discrete mathematics explanation does not in any way contradict what you did in remedial algebra. It probably just gives you a more thorough explanation. So let's move on to the next thing. So the next thing is a little bit of, we're going to start some logic notation, and we're eventually going to get into conditional statements and things like that. So make sure I got some ink in this one. If I make a statement, okay, a statement is either true or false, but it cannot be both. For example, my statement is, I am standing here. That's either true or false. Okay, I am standing over there. Well, that's probably false because I'm standing here. a statement can't be both true and false at the same time. Okay, that's what it is called, a contradiction. And I want you guys to get familiar with that term, because that's going to be really, really commonplace. And we're going to talk about it today. In fact, a contradiction is when something and its negation or complement are both claimed to be true. In other words, I am here, I am not here. They both cannot be true. Only one of them can be true, right? In a court of law, you are guilty or you are not guilty. You can't be both. Right? So that not is kind of important. So when I have a statement, we'll call the statement P. And let's say we have another statement called Q. These are not sets, these are actual statements. All right. So I have two different statements going on. So what if I said, one of my statements is, I am here. The second statement is, the television is on. Okay. They could both be true. They could both be false. One of them could be true. One of them could. There's a lot of possibilities. So if I said, let me consider all the possibilities of these. Now, even though these are statements, the visual sometimes makes it much, much simpler. Okay, then the part in between, this is be where both P and Q are true at the same time. That's called the intersection. We're very familiar with that. But this part here would be, the notation we use is P and Q. Now, what's funny is when we use set notation, in set notation, I have two sets. That's the symbol for intersection. When we're making statements, we don't use the intersection symbol because intersection would be two sets where they overlap. These are two statements. There are no things. You know, there's no A, B, and C. So this statement is true and this statement is true at the same time. I can represent this way. So in other words, it's still an intersection. It's just the context is a little different. I don't have a set of things. I just have a statement. Now, what would this be? Well, if a statement P is either true or false. It doesn't matter. But if I then say this, that means not P. No matter what P is, the squiggle in front means not P. So if the statement P is I am here, then the squiggle in front, it does not mean I am somewhere else. It means I am not here. You just simply do the not. All right. If the answer to the question is x equals 3, the squiggle would mean the answer to the question is not x equals 3. It doesn't mean it's a different number. It just means it's not that thing. So the nice thing about the squiggle is that every single thing is or it is not. That covers all situations. So this part here would be what? This would be, I'll use a different color so it's easier to keep track of. This part out here, that would be P and not Q. And if it helps, you can put it in parentheses. Oh, then what is this part out here? That part out here would be not P and Q. Okay, so that would be this, that would be this would be this. Now, what would we call it if it comes from all of this? That would be P or Q. And much the same way the notation we used for sets, that's intersection, that's union. And an easy way to remember, intersection always was and, union always was or. And a lot of times we get confused on the difference. And or are extremely different in their meaning. One is considered exclusive, one is considered inclusive. And it's very important that we distinguish the difference. So if I'm talking about the entire thing here, that would be the union. So that would be the or. Because if I'm here, if I said you can be in P or Q is true, I could be P and not Q, I could be Q and not P, and I could be both. It does not exclude the intersection, by the way. That's very important that we recognize. So the example I like to use to make it really clear the difference between an and an or. Now, if you're computer programming, it's and an or and not are the three most important terms, okay? And, or, not. Okay, I'm going for a job interview. Okay, so I did an application to a company, big company, and now I'm showing up for the interview, and there's the long table of the interrogation committee. And I tell them, before I accept your job offer, they haven't actually interviewed me yet, by the way. Before I accept your job offer, let me give you my list of demands. Okay, I want the 6-figure salary. I want my own parking place. I want keys to the executive washroom, and I want the letter M stricken from all company language. And so then they get together and they talk about it, and they come back to me and they say, well, we can do everything except the parking place. It's kind of crowded. Will I accept that job? Anybody tell me the answer to that? It's black and white. It should be absolute. Will I accept that job?
You said and, right?
Oh,
So therefore, no.
I said and, therefore the answer is no. Because and is extremely exclusive. When you use and, if any part of the statement is not true, then the entire statement is not true. So I said this and this and this and this, one of them wasn't true. That would mean you're not in the mutual intersection. So I just drew a picture with 2, but what if I had 3 or 4 or 5 circles? And starts getting more and more difficult to achieve. So when you make an and, everything has to be true or the entire thing is not true. Now, I come back a week later, tail between my legs for a second interview, and I decide to change my list of demands. So I say, okay, the 6-figure salary, or the parking place, or the keys to the executive washroom, or the letter M thing. And they come back to me and they said, we can do the keys to the executive washroom. Will I accept the job now?
Yes.
Yes.
Yes. Or is very inclusive, meaning if any part of an or is true, the or is true. If any part of an and is false, the whole thing is false. That's really, really important that we understand the difference. So when you say or, I could have all sorts of conditions. Only one of them has to be true for the or to be true. Now, if all of them are true, that's great, but only one has to be true. If I give you an and, if anything, and by the way, we're generally not going to do 5 or 6 statements. We're usually going to work with 2, 3 at the most. But if any part of the and is not true, then the and is not true. Then the overall statement is not true. So let's do some simple statements so that we understand. And there are parentheses involved in some cases, and we want to talk about how that works. Because we're going to talk about statements now. Later, we'll talk about sets. Statements are a little easier to conceptualize because with sets, you have to think about listing things and such. Now it's just a statement is true or a statement is false. And if a statement is true, then putting the squiggle, that's called the negation. Then the negation would be the opposite. So if I give you a false statement, the negation would make it true, and so on. So let's suppose that P is that you ate breakfast. And let's say Q is you, okay, make sure you are muted, guys, unless you're answering a question or something. Let's say you watched television. And let's say that R is you went for a walk. Okay. We symbolically now, I want to write you ate breakfast and went for a walk, but didn't watch TV. I want to say that symbolically. So we have the symbols and or negation. Now, I want you all to think about this for a moment. You ate breakfast and went for a walk, but didn't watch TV. So, ate breakfast and went for a walk. How would I say that? Ate breakfast and went for a walk. So, how about P and R? But didn't watch TV. That would still be an and I didn't watch TV. Anybody want to try that one?
Could you do and not Q?
And not Q. Beautiful. By the way, the parentheses in this case wouldn't be strictly required. It just makes it easier to read when you have multiple symbols in a row. It's kind of like in algebra when you have minus the negative or something. if you're entering it on your calculator, you don't need parentheses, but when you're writing it out, parentheses are really for readability. So these two are together and not this. Now, there's nothing complicated in that, but it does matter because if I throw in the or the not or different things, the question is, do things distribute? I mean, can I say something? So let's go back to a picture like we did earlier. Excuse me. I would like to know, go back to the Venn diagram. Let's say that's P. Again, you guys make sure you're muted. First thing is, what would I call this area out here, or this set of things out here? I want to describe the blue using the notation we just did. Oh boy, this is kind of tricky. I want to describe the blue using the notation we just did. Well,
Not P and Q.
okay, so walk me through it. You said not.
And then parentheses P and Q.
P and Q, okay. Is everyone happy with that?
Correction,
I
sorry,
think
P
it would be
Q.
or.
Yeah, or.
Ah, okay, so what's between the circles? What's in the circle area? Do we agree that's the or?
Yes, that was my bad, Professor.
And so the blue would be not the or. Now, is this the same? And by the way, here's the symbol we use to represent it's the same thing. We talked about this yesterday. The 3 bars. Remember, I said the 3 bars also means in this context equivalent. 2 things are equivalent, which by the way, doesn't violate calling something a definition, because if I'm defining something, I'm giving you something that is an equivalent meaning. Think about looking up a word in the dictionary. You're looking up a definition. Aren't you getting an equivalent meaning of the word? So that's not a violation of the 3 bars. Question. Is that true or false?
It's false because you
False.
need a negation on Q.
So the negation on Q, do you agree would be everything outside of Q? That's the negation on Q, everything outside of Q. So if I said, let's negate Q, or excuse me, I'm sorry, P, everything outside of P or Q, wouldn't that be basically the entire thing or Q? That would put me in here. Oh my goodness. So this statement right here would be everything except this little, crescent moon. And that's not what I want. In fact, I don't want any part of Q, do I? So perhaps, if I'm out here in the blue, I should be outside of Q too. So this is better. Do you agree that's better? But is that still it? Everything outside of P would include part of Q. Everything outside of Q would include part of P. So that may still not be it. I need to be outside of Q completely and at the same time outside of P completely. Oh. Now try that one. Will that work? So here's what I'm going to do. I'm going to draw that picture right now. This is why I love the Venn diagrams. All right, let's start with everything outside of P. Everything outside of P. Okay, you all agree that's everything outside of P? Now let's add to that everything outside of Q. Now let's only look for the and, the mutual. So that would be kind of like the blue and orange. That's only blue. That's not it. That's only orange. That's not it. But the stuff out here is both. So what did I just come up with? Only the outer rim. So we can now see from a pictorial standpoint, we can see that those are the same. We're going to prove it a different way. This is one of what are called De Morgan's laws. There's a couple of them. This is one of the things called De Morgan's laws. Not or is the same as and between the knots, if you want to say it that way. So, okay, I'm going to go to the store or I'm going to take a nap. I'm going to go to the store or I'm going to take a nap. What's the negation? I am not going to go to the store and I'm not going to take a nap. That's what this is saying right here. And it's really, really powerful. Now, this is the simple pictorial way of looking at it. We now want to do it from a mathematical standpoint. So I'm going to introduce something to you that I think you're going to like, called a truth table. Now, some of you may have done this. If you've had a philosophy course, you very well may have done this. That's the only other place I think I've ever seen a truth table. And it's only if you got really lucky that you had a philosophy professor who actually had logic classes in their background, because that's not always the case. A truth table is basically a table of truths and falses. I mean, it's actually that simple. So if I said, for example, let's say I have two statements, P, and I have the statement Q. Okay, I'm going to leave some room here. P is true, Q is true. P is true, Q is false. P is false, Q is true, or P is false, Q is false. These would be the only possible outcomes if I have two statements. They're both true, this one's true and that's false. Okay, so I'm introducing, this is what a truth table would start with. Now, let's do the next set. What about not P and not Q? Okay, well, then that would be false, false, true, true. That would be false, that would be true, that would be false, that would be true. And there's no real mathematics going on here. That's a fairly simple notion. What about P? What was it? Oh, I'm running out of room. I'm writing too big here. What about P or Q? Okay, now P or Q, remember, if any part of an OR is true, then the OR is true. P or Q. Well, it's clearly true. P or Q. That's true. P or Q. That's true. P or Q. That's false, because neither one of them are true. Okay, you with me so far? How about, let's do not P, I'm running out of room here, and not Q. It's getting a little bit tight. I have room for one more. Not P and not Q. So now I'm looking at these. Now remember, for an and to be true, the entire thing, both of them have to be true. Not P and not Q. False, 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 true. And now the last one we're going to do, not P or Q. That's actually easy, because remember, a not just means change what it is. There's my P or Q. So not P or Q, false, 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 true. Okay, we've just done a fairly complicated truth table to prove. This is the formal mathematical proof of De Morgan's laws. Say, where's my proof? The column here that goes with that statement and the column here that goes with that statement. Remember, we were comparing these two statements, right? Not the or and the and of the nots. That's what we just did a moment ago. They have the exact same, we call them the truth values. The trues and falses are exactly the same in the same place. That means that we have just proved that not P and not Q is equivalent to not P or Q. So one of the simplest ways of attacking things are, if you're asking, here's a statement with, ands and ors and nots, is it true? You can't prove it by examples. So let me think of statements and see if I can show it's true. No, you prove it using a truth table. You write down everything you need to in order to get the truth table for this, or I said the column of the truth table for this, the column of the truth table for this. If they're absolutely identical, then the statements are in fact equivalent. Whoa. I mean, that's kind of a crazy notion here. Okay. So again, that's the first thing. There's a whole lot of mathematical statements that we're going to be able to show in time. I like that one because it's simple. Now, I want to look at something fairly simple notion. Start with something really simple. Let's start with P, not P, P and not P, P or not P. I want to make the truth table for this. This is a pretty simple truth table because I only have P, so P is either true or false. This is fairly easy. A lot of times people like putting columns. I don't care. As long as you leave enough space between, you don't necessarily have to write columns. Now, P is either true or it's false. Then not P would be false or true. They got to go hand in hand. P and not P. Okay, well, this is true and this is false. This would definitely be false. If this is false and this is true, then this would definitely be false. Okay. P or not P. If this is true and this is false, the or would make this true. This is false and this is true, so the or would make this true. Now, I'm going to relay something to you. Now, I did a very simple one. I just did P and not P. I could have made this complicated, P and Q and not this one. We could have like 10 different things going on. We could have 20 columns. That's great. Whenever you have a situation where you have an entire column that is false or an entire column that is true, if you have either one of these cases, this is a very powerful mathematical statement. If you ever have a situation where the entire column is false, you have a contradiction. Okay, an entire. So I said, I am here and I am not here. That's clearly false. But if you have a situation where an entire column is true, that means you have something that's absolutely true no matter what. There's no way you could ever have a false situation. This is called a tautology. Tautology. Everything's false, you have a contradiction, meaning, again, you're trying to claim something and its negation are simultaneously true. That's impossible. But in the second case, I am either here or I am not here. I'm pretty sure that's true because it doesn't leave anything else. My glass of water is full or it is not full. That's true because it doesn't leave anything else. So everything false in a column, you have a contradiction. Everything true, you have a tautology. And these are powerful statements. And it's not very difficult to come up with a situation where you actually have one or the other. So sometimes we're asked, are two statements logically equivalent? We'll do this. We'll do a truth table and compare columns. Other times I'll give you a statement and say, is this statement a tautology? Is it a contradiction or is it neither? By the way, everything is not a tautology or a contradiction. Only certain things are. So let me grab some problems out of the text. Okay, so let's consider this stuff here. Truth tables are kind of fun. I mean, there's no calculation involved, and I'm just sort of reading the end. So, sure I can read this. Okay, so the first one we're going to look at, sorry, it's hard to read. Hold on, too many variables. Let's do this one. P or P and Q. P. I have two different statements. The statement on the left and just P. Is this statement here exactly the same as the statement here? Are they logically equivalent? Okay, I don't know. I'm not even going to try to figure it out. Well, let me just think of things in my head and see if I can, hash it out. No, we're going to make a truth table. So what must be in my truth table? I need P. I need Q. I need P and Q. I need P or P and Q. And then just for good measure, I'm going to put P again at the end because then it's easier for me to compare the two. Okay. Generally speaking, whenever you have statements that you're trying to determine if they're logically equivalent, you want them to be the last two columns. It just makes it easier. You don't want to be, trying to look across the room. So let's put the proper trues and falses as they go. Usually you want a nice little organization. So I'm going to go true, 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 false, false, true, false, false. I've just covered every possibility for P and Q. Now, P and Q. Well, that's the only one that's going to be true because it's an and, so these three would automatically be false. Okay. P or P and Q. So now I'm going to compare these two columns, and because it was an or, I only need one of them to be true. So that's true. That's true. That's false. That's false. Now I'm going to restate P so I can compare them side by side. Do we notice anything, folks? They're exactly the same, aren't they? They don't all have to be true. They just have to be the same. Because they're exactly the same, that means this statement here is equivalent to that statement there. Wow. Okay. Now what I'd like to do is show you a simple representation using a Venn diagram. Even though it's true, it's always good to convince ourselves. So there's my P, there's my Q. P and Q is right here. P or P and Q would be P or P and Q. Well, I think I've just pretty much covered up P because that was our result. Oh, okay. That's kind of easy to see now, isn't it? But if I had had more symbols here, more statements, P, Q, R, S, T, that would have been really, really challenging. But this was actually fairly simple. All right, let's do another one. Let's look and see if something is a tautology or contradiction, perhaps. Okay. Let's do, my light is not great here. I want to not P or Q, or P and not Q. All right. I'm just giving you a mathematical statement. I'm not comparing it to anything else. I would like to know, is this an absolute truth no matter what P and Q are? Is this an absolute falsehood, contradiction, no matter what P and Q are? Or is it just somewhere in between? Okay, most statements are neither tautologies nor contradictions, but all I have to do now is come up with a truth table for this. Okay, it's going to be fairly long, so you probably want to write a little bit smaller. And the nice thing is there's no interpretation. You just put the truths and falses where they will naturally fall. So that's why I say most people like truth tables, just because there's no complication. So I'm going to need a P, a Q, a not P, a not Q, an or, an and here, and then the big thing. So that's, I think, 7 columns I'm going to need. So I'm going to write a little bit smaller. So P, Q, not P, not Q. Now I need this one, not P or not Q. I need this one, P and not Q. And then I need the whole thing. And I'm just going to write the whole thing. How's that? Because I don't think I can fit that on there. So this means I have 7 columns. Yikes. And what I'm actually looking at, in this case here, I am only going to be looking at this column. Either it's all true, it's all false, or it's a mixture of trues and falses. Those are my only possibilities. So let's check it out. So,
Professor, quick question.
yes.
That not P or not Q, where did you get that one? Because the first one is not
Did I write
P
it
or
incorrectly?
Q.
Not P, not, oh, I'm sorry. Thank you. That should be, yes. Thank you for that.
Awesome, thank you.
I'm the only one who can't see that. let me move that Q a little closer. Yeah, that would have, whoops, let me try that one more time. That would have not worked so well. That no work, as my wife would say. That no work. All right, so true, 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 false, false, true, false, false, piece of cake. These guys, just be mindful so you don't somehow, and by the way, I don't say this one jokingly. This is the universal problem that students have when they're doing trues and falses. I start getting a lot of these. The ambiguous, I'm not sure what it is. In other words, I know what the answer is, but if you can't read your own intent, that's probably not a good thing. So I say, be mindful that your T's look like T's and your F's look like F's, and you don't start having symbols that you can't distinguish which one's which. And you might be laughing at that. No, when I get these quizzes turned in, I'm going to say probably at least 25% of them will have ambiguous symbols that no human being could interpret. And therefore we're going to get incorrect conclusions because the writer, what some people do is they'll do this. They'll do small T's and F's. I don't care. Just make sure that you can read them. It is kind of silly to mess that up because we're careless. All right, this would be false, true, true. Not P or Q. Now, please go slow. Make sure you're looking at the right columns. Not P or Q means I'm looking at these two columns. Order does not matter, by the way. So it's an or, so that's a true, that's a false, that's a true, that's a true, because it was an or. P and not Q. So now I'm looking at these two. Let's see, do I have any that are true? Yes, only this one will be true because it's an and. So this will be false, true, false, false. So far, so good. Now I've got a bunch of T's and F's and everything I've said is correct. But now what we want to do is say, what is the column for this? So now I'm comparing these two columns with an or. So that would be true because it's an or. That would be true. That would be true. That would be true. My conclusion is based on the last column only. That means this statement here is in fact a tautology. This statement here is absolutely true no matter what P and Q are. Not P or Q, and P and not Q basically is always true. Isn't that crazy? So somehow or another, you got, like, I have a P and a not P, or P or not P. I have ors and ands in all the right places. Now, if I changed any one symbol, if I moved any of the negations, it probably would not be a tautology. Could I make this so that it is a contradiction? Sure, I can rearrange things so that it's not true. But it would actually have to require a little bit of cleverness here. So this is the introduction to how to do a truth table. Now, next day, we're going to go much further, and we're actually going to start almost sort of in an equation form, say, now, is there a way that I can manipulate this almost algebraically by doing things like applying De Morgan's laws and some of the other laws? Yes, that's sort of reserved for next day. But today, big picture is, can you come up with a simple truth table? And we're going to use truth tables all throughout this course to help us prove things because they're so practical and they're so easy to use. Okay, so if we're comparing two statements and saying, are they logically equivalent? They are if they have the same truth values in their columns. If I give you a single statement, I'm not comparing this to anything else. I'm saying, is this absolutely always true? Is this absolutely always false? Or is it somewhere in between? Then I'm just basically looking at that last column. So kind of different goals in mind here, but that's where we want to get to today. So I will stop recording.